Hello, welcome to my video series of algorithms. This is the first video of Module 4, Greedy Algorithms. In this video, we will discuss the intuition and basic idea of greedy algorithms. Let's motivate the greedy algorithms using the trajectory of a person's life. We know life is full of choices. In our life, we must make a series of decisions. For example, whether to go to college, whether to go to grad school, which job to choose, buy or rent a house, and so on. Most of us hope to achieve a goal through making correct decisions. For example, say someone's goal is to become as rich as possible. Perhaps one of the most important choices the person has to make is after graduating from college, whether to continue to a higher education or start working immediately. Since the person has an end goal of being rich, we can evaluate the pros and cons of these two decisions in terms of wealth accumulation. If the person continues to higher education, he or she may lose money now because of the tuition paid and no time to work and earn money. On the other hand, a higher education degree could qualify the person for a high-paying job in the future. If the person decides to work immediately, he or she will start earning money now, but may lose the opportunity of having a high-paying job in the future. For the first strategy of going to higher education, one considers the wellness of the long run. In other words, it tries to achieve global optimum. For the second strategy of working immediately, one considers the wellness of the present. In other words, it tries to achieve local optimum. One simple yet myopic decision-making strategy is to always align the short-term outcome with the end goal. For example, one may choose to work immediately because it allows one to gain money right now, which is consistent with the end goal of being rich. In other words, such a decision-making strategy only considers local optimality, but does not consider global optimality. As a result, we term such a decision-making principle greedy. The algorithms that are designed based on this principle are called greedy algorithms. Now, we can describe greedy algorithms more formally. Greedy is a decision-making principle that can be used to solve computational problems. We know that each computational problem has a math objective, just like the person in the previous example, whose math objective is to maximize his or her wealth. The greedy principle attempts to achieve the math objective through a series of decision-making steps. For example, the series of steps could be the decisions the person makes in his or her 20s, 30s, 40s, and so on. In each step, it tries to align the present outcome of the decision with the math objective of the problem. In the previous example, a greedy algorithm would choose to work immediately as it is consistent with the goal of being wealthy. Finally, we should know that a greedy algorithm only aims at achieving the local optimum, but not the global optimum. As a result, one important caveat we should mention is that the greedy design principle does not guarantee a solution to the computational problem. In other words, a greedy algorithm is not always correct and can be wrong sometimes. But in some special cases, if the global optimum of the problem happens to be the same as the local optimum, then the greedy algorithm is correct. However, the property needs to be proven. Nevertheless, even if a greedy algorithm turns out to be wrong, it can still serve as an approximation algorithm that produces a useful suboptimal solution to the problem. Designing a greedy algorithm is often intuitive. We just need to make a plan that aligns the outcome with the overall math objective. The resulting algorithm often runs in phases. Due to the simplicity of the design, the time and space complexity should also be easy to analyze. However, the difficulty of the design is to prove that the greedy algorithm is correct. In other words, showing that the local optimum of the problem is the same as the global optimum. Now, let's look at one real problem and try to solve it using a greedy algorithm. In addition to familiarizing you with the design process, we also hope to show you that greedy algorithms are not always correct. Consider the knapsack problem. Suppose you're going hiking with a backpack, and you decide which things you would bring to make your trip as happy as possible. You could bring water, snacks, an umbrella, a handheld gaming console, and so on. Different items can satisfy your different needs, and say we can quantify these needs into happiness scores. In this case, you should maximize the overall happiness score of the items as long as your backpack can hold. Formally, you are given a total capacity limit C and a set of items I. Each individual item I in the set I is associated with a weight Wi and a value Vi. Here, you can think of Vi as the quantified happiness score. Now, you are asked to find a set of items I prime, which is a subset of I, such that the sum of the weights of the items in I prime is within the limit C, and at the same time maximize their total value. Here is a specific instance of the problem. The capacity of the knapsack is 12. We have 4 items to choose from. Their weights, values, and per unit values are listed here in the table. Recall that the knapsack problem has 2 objectives. One is to maximize the value, and the other is to minimize the total weight such that it is smaller than the capacity. Therefore, we can naturally come up with 3 greedy strategies to implement when selecting each item. We can pick the most valuable item, the lightest item, or the item that has the highest per unit value. Let's see what solutions would each of these strategies produce. First, let's try picking the most valuable item from the set. We will pick item 1 as it has the highest value of 16. Then, we cannot pick any other items, since it would go beyond the limit of the capacity 12. The algorithm would terminate here, and the total value we have is 16. It is incorrect, as we can pick items 2 and 3 to reach a total value of 23. Second, let's try picking the lightest item first. We will first pick item 4, which is the lightest and has a weight of 5. Then, we will continue picking item 2, since it is the lightest of the remaining items. Note that item 3 also has the same weight, but we can break the tie using their values. The algorithm would terminate here, as we cannot include any more items without exceeding the capacity limit. The resulting total value is 22, which is also less than the optimum of 23. Finally, let's try picking the item that has the highest per unit value. We will first pick item 2, and then item 4. The algorithm would terminate here, resulting in a total value of 22. It does not achieve the global optimum of 23 either. From the above example, you can see that we cannot design any greedy algorithm that can achieve the global optimum. It demonstrates how greedy algorithms could fail in some cases. As a result, I would like to emphasize here again that the correctness of the greedy algorithms is not guaranteed and needs to be proven rigorously. Fortunately, there exist some problems that can be solved optimally using greedy algorithms. We will present some of these problems and their greedy solutions in the remaining videos of this module. The problems include the shortest path, minimum spanning tree, clustering, interval scheduling, minimized maximal lateness, optimal caching, and Huffman coding. In summary, we have discussed the basic intuition and design process of greedy algorithms. We know that they implement a myopic decision-making principle, which only considers local optimum rather than global optimum. As a result, they may not work for all problems, and only work when the local optimum of the problem is consistent with the global optimum. In the next video, we will discuss the shortest path problem. Thank you for watching, and see you next time.